Okay, so folks, we're going to take a look at page 146, number 13. So let me read out the questionnaire here. Let me show it to you. Okay, so it's similar, I think, to the one we did in class where we have an isosceles trapezoidal prism, okay? And we want to try to maximize, again, the cross-sectional area. So again, the cross-section is going to be, this here, the base of this prism, which is the trapezoid. I guess the difference in this question here is the three lengths were fixed, and it was the angle that was variable. Whereas here, they've kind of switched it around, as they've said that the angle has to be 120 degrees on either side at A and B, but the way in which we fold it can be different. So it could be kind of long with sort of short flaps going up and down, or it could be like this, a small base with longer flaps going up. So our goal is to figure out what's going to give us the maximal area. Now, hopefully you can see that this 5 meters is descriptive in terms of telling us what this thing looks like, but it's not going to affect our problem, because what we're trying to do here is just maximize the area of the base, which is the trapezoid. All right. So let me try to set this up. It's what do we have? 60 centimeters. Okay. So even though they give me that other thing in meters, since I'm only dealing with the area of the base, I think I'm just going to stick to centimeters. Okay, so let me draw a diagram here. And what we have is that this is 120, this is 120. Okay, and what I don't know, I know that the total of these three has to be 60 centimeters, but I don't know exactly what they are. So again, this is kind of almost like the opposite scenario as what we saw in class. Okay, so I think what I'll do is, since there's two of these, why don't I call these two X? And so since the total is 60, this thing here is going to be 60 minus 2X. Okay, I just feel it's easier to work with, the one with two sides, make that the simpler variable expression. All right. And so now what we want to do is we want to write down what we're trying to maximize, which in this case here is the surface area of my trapezoid. Okay. And of course, we know that that's given by, so, let me draw my diagram here, that if this is the height, and we'll call this B and we'll call this A, we know it's A plus B times H divided by 2. So this is what we're trying to maximize. And of course, there's lots of variables here. And so it looks like I'm going to want to try to put everything in terms of X. Okay, now I already have this little A value in terms of X. So that's done. The B value, well, again, very similar to last time. This portion is going to be the same as this, so 60 minus 2X. So I just have to determine these two side lengths, which again, I notice are the side lengths of this, is the adjacent side to this right angle triangle. And then the height is also a side length in this right angle triangle. All right, so I think I should have enough information to write everything in terms of this variable X. All right, any questions so far? No? All right. So what do we have here? We have that, I guess we'll find the height. So it's going to be sine of 60 degrees is equal to H over X. And so H is equal to X times sine of 60 degrees. Now you might be wondering, why am I using degrees and not radians? Well, because I actually have it. So I'm just going to be calculating it. All right. It's not like it's a variable and I need to be working radians so I can take the derivative. Okay. And since I'm working with 60 degrees, I might as well draw myself a little triangle on the side. So 1, 2, root 3. And so sine of 60 is root 3 over 2. So h is root 3 over 2 times x. All right. And now let's do the same thing for this little portion. Let's call this, I don't know, let's give it a name. Let's call it b here. Okay. So here we have cos of 60 degrees is equal to b over x. And so b is equal to cosine of 60, which is 1 over 2 times, multiply that to the other side, x. And now I'm going to use this. Oh, I guess I shouldn't have called this here. I'll call this big B, just so that I don't confuse it with the little b there. All right. So now all I'm going to do is I'm going to take what I found here and stick it into my trapezoid formula. So A, we already said, was 60 minus 2x. Okay. And then plus B, which is this thing here, which is another 60 minus 2x plus these two sides, which were my half x. So plus half x plus another half x. Okay. All of that times the height, which we determined was root 3 over 2x. And then all of this divided by 2. Okay. So while this, looks a little complicated, essentially I just did exactly what I did last time, is I put everything together, except instead of using my variable, my angle as my variable, I used one of these side lengths as my variable, because that's the thing I don't know. Where did the minus 2x? Because remember, this whole sheet has a length of 60 centimeters. Okay. So if this is x and that's x, they have to be, because it's an isosceles trapezoid. So this thing is just the whole thing 60 minus these 2 bits. All right, is that okay? All right. So this actually doesn't look like a tough function. It just looks like something we're gonna have to simplify here. So here, what do we have? We have 60 plus 60. So we've got 120. Here we got -2 minus 2 is -4 plus 1. So minus 3x. Okay. Then here, this 2 can join that 2 in the denominator. So this root 3, I might as well put it at the front. And then here I've got another x all over 4. Okay. And somebody says, could you explain how you're able to use the special triangles? Oh, because 60 degrees is one of my special angles. Okay. So this is the 60-degree special angle. Okay. Sorry if it's a bit small. I just can't. I'm going to try to bring this down a bit, but there we go. That's my thing at school is a little unsteady. All right, and I would even clean this up a bit more, because I definitely don't want to use the product rule. So I've got my root 3 over 4 here, which is just going to be a constant. And then what do we have? We have 120x minus 3x squared. Okay. And that looks fine. All right. So any other questions so far? And so now we have our thing, and I guess x has to be, well, it's got to be bigger than 0, and it's got to be, less than, well, I guess since there needs to be 2 of them, I guess it actually doesn't have to be less than 60. It has to be less than 30, right? Because since there's 2 of these sides, at most it's got to be, half of the whole length, which is 60. Okay, but again, it's a open interval, and so I'm not going to be able to use the closed interval approach. All right, so let's take a prime. This is just root 3 over 4. All right, so what do we have here? We've got, this is going to be 120 minus 6x. Okay, and of course we want to make that equal to 0. And so here I have x is going to be equal to 120 over 6. And of course, that's equal to 20. And hey, I notice 20. It means these sides are all going to be the same if this is indeed a maximum. Now, who can tell me why I don't need to do a number line here to know that this is going to be a maximum? By the way, it is in my domain. Who's going to tell me quickly why I don't need to do any work here to show that it's definitely the absolute maximum? Zaveri or Kether?
I can go if you don't mind, Tony.
Yeah.
The reason why you don't need to do a number line is because this is basically a quadratic equation.
Okay.
So basically from here, we notice that we have a negative coefficient, and because it's a negative coefficient quadratic equation, therefore we know that this point is going to be a max.
Very good. Okay, so there we go. And kind of a similar, you see a very, simple A, the area function is quadratic with a leading coefficient that's negative. So that's all you need to say. So I'm going to go back now to my question to see exactly what they're asking me for. It says then determine the dimensions so that the cross-sectional area will be at a maximum. Okay, therefore, I guess all three sides will be 20 centimeters. Okay, and that's because 60 minus 2 times 20, 60 minus 40 is also 20. Okay, and there you go. Now, this is how I'm talking about the dimensions. I guess they might also be talking about height and A and B, since we are talking about a trapezoid. But here, this would seem to be the more reasonable thing to give, because what it tells you is how much I'm going to be bending over on each side in order to create this trapezoid, which is more useful information than knowing the height and the two bases. All right. Any questions on this here? So just as a recap, as you're thinking about questions, is notice what I tried to do. I just tried to set up exactly the same thing as I did last time. So again, we try to use what we've seen before as a model. I just had to switch things up a bit because it wasn't the angle that was variable. It was these three parts of the trapezoid that were the variable. Okay, but in the end, I used the exact same procedure working with this right angle triangle to help me write all the pieces in terms of the same variable. All right, any questions here? I don't know. Somebody asked, well, something on the test, and obviously it would be, a thinking type question. It's maybe a little long for a test question, but, I can't say that it won't be on it. Okay. All right, so let's go to number 16. So this is one of these driving ones. So let's take a quick look at 16 here. Okay, so north-south highway intersects an east-west highway at point P. And we're measuring when one car kind of drives eastward from point P. And then at the same instant, another vehicle is 5 kilometers north, so somewhere above P, and then is driving south towards P at 80 kilometers an hour. And we want to see when the two vehicles are closest to each other and the distance between them at this time. Okay, so let's take a look at this. So this, again, I would say is almost identical to one of the ones we did in class. So page 146, number 16. So let me try to draw my diagram. So I've got, since everything is, from the north and then going east, I'll draw point P here. So I've got one car. And remember what I want to do is I want to try to just represent on my diagram some moment in time after 1 p.m. So at some point after 1 p.m., car A has traveled some distance towards the east, and car B started 5 kilometers north, okay, and moved some distance towards P. All right, so this is some generic moment in time, and what I want to do is I want to minimize the distance between them. So this is what I'm trying to minimize, okay? And this is the scenario. Now, since they're talking about at what time this is happening, it makes sense to let t be our variable. So we'll say time from 1 p.m. All right. And because we know the time and we know the speeds, we can calculate expressions for these distances. So car 1 travels at 60 kilometers an hour. So this car would have traveled 60 t kilometers. Okay. The other car is traveling at 80 kilometers an hour. So the distance it would have traveled was 80 t. But of course, I'm not interested in that distance. I'm interested in the one that closes off my right angle triangle. So this will be a total of 5 minus 80 times t. All right. And now, because of Pythagoras, I now have a nice way of writing this distance. All right. So what I'm trying to optimize here is the distance, which is going to be the square root of the sum of the squares of the other two sides. So it's going to be 60t squared plus 5 minus 80t squared. And they don't really give us, I suppose we could figure out how long it takes for this car to reach point P. Okay. So if we need to figure out an endpoint, we will, but let's say here t has to be greater than or equal to 0 for sure. Okay. And then we'll kind of see what happens if we need to calculate that time. I guess we should do it. So 80 kilometers sorry, 5 kilometers at 80 kilometers an hour. So again, remember, if you're not sure, V equals D over T. And so if you're looking for the time, T is equal to, just do a little change, D over V. Okay, so what is 5 divided by 80? 5 divided by 80 is 0.0625. So if we want to be really clear here, 0 less than or equal to t less than or equal to 0.0625. And of course, this is in hours. I'm just keeping everything in hours. Okay, but now we have our variable, our equation in terms of one variable. Let's take the derivative. Okay, so here, of course, we're going to have to use a chain rule. So 1/2 this whole thing, 60t squared plus 5 minus 80t squared, all to the negative 1/2. So all of this is going to end up in the denominator. Okay. And now when I take the derivative of this inside function, I'm not going to bother multiplying it out. I'm just going to use a chain rule on this here. So this is like u squared. So 2 times 60t times the derivative of 60t, which is 60. Okay, you see how the chain rule makes that pretty easy. Plus, again, the 2 is going to come down, 2 times 5 minus 80t times the derivative of this inside function, which is just going to be negative 80. Okay, now notice here how I can factor out the 2 and reduce it with the 2 in the denominator there. So that'll at least make my life a little simpler. And of course, I want to make this derivative equal to 0. So 60 times 60, I guess, is 3600 t minus 5 times 80. 5 times 8 is 40, so minus 400. And then here, 80 times 80 is 6400, so plus 6400 t all over this big square root. I'm almost tempted not to write it out, but for good measure, I'll write it all out. Okay. But of course, I don't care about this denominator because I could just multiply to the other side. So essentially, I just have to work with this numerator function. So 3600 plus 6400 is 10,000 t. Bring the negative 400 to the other side. Okay. And it looks like T is going to be equal to 400. Oh, sorry. It looks like it froze. There we go. Over 10,000. Did I get that right? Yeah. So get rid of those two zeros. So 4 over 100 is 0.04. All right. Any questions up until this point?
Yeah,
Arthur?
Tony. Yeah,
Yeah.
I have a quick question about this. So, couldn't we just, cancel out the square root? So we just square both sides. So it'll be d squared, and on the left side, and it would just be 60t to the power square to the power 2 plus 5 minus 80 to the power 2, and then we
Yeah.
could just solve the derivative for both sides, and then
Yeah, the thing
That's an
here is
easier
we
way,
haven't
right?
really, well, yes, but we haven't actually talked about how to take the derivative of d squared with respect to t. So if you can figure out how to do that correctly, then that is perfectly fine. And we're going to see that in tomorrow's lesson, how there's an alternative to this here.
I mean,
Okay.
this one seems pretty simple. Just it's gonna bring down the 2, and then no, never mind. Okay, thank you, Tony.
I'd have to see what you did to make sure
Yeah.
you showed all the steps correctly. Okay.
Okay,
I'd
thank
have
you.
to make sure you were showing all those steps correctly. But for those of you who might have seen the video, you would have seen that there's an alternate way of looking at this that, does make it a little more simple. Okay. Not too much, but a little. Okay. So now here, I guess we have to, so we have a closed interval. So we could just check that. Okay. Check all the different possibilities and see that this is indeed the shortest. So I'm going to check D at 0, D at 0.04, and D at 0.0625. Okay. Okay, so that first one would be pretty easy because when I stick in D equals 0, that goes. So I have the square root of 5 squared, which is just 25. Nice and easy. Okay. Now, notice here at 0.0625, I think this thing's going to go to 0, but let's just do it here. So what do we have? We have 60 times 0.0625 equal, and we're going to square that. Where's the square on this calculator? There we go. Okay, and then we're going to subtract. Oh no, I have to add. Sorry about that. There we go. We have to add this thing here. So 5 minus 80 times 0.0625. I'm trying to make sure I don't make any silly mistakes here. Squared. And then I have to take the square root of that. So I'm just going to do it as exponent 0.5. Okay. And so here we have 3.75 already. Very, oh, sorry, that's this one here. I just did this one here, 3.75. So I did the endpoints. So obviously that's much closer. And now let me do 0.04. Okay, so 60 times 0.04 squared. Okay, plus.
Only the 0 to D of 0 should be 5, not.
Oh, 5. Oh, because the square root of 5 squared is 5, not 25. Good call. Thank you very much. You see here, that goes to 0. I'm just left with 5 squared. Square root of 25 is 5. Thanks for noticing that. Okay, so here, where was I at? So 5 minus 80 times 0.04. Okay, all squared. And then the square root of that is just 3. And there you go. There's my answer. Okay, so when does it happen? Now, let's see what it's asking for. It says, find the time. So I guess we could say, time is 0.04 hours after 1 p.m. Or we could be more specific and figure out exactly what that is. So what is 0.04 hours? 0.04, and of course there's 60 minutes in an hour. So that's 2.4. So it happens at about 1:02 PM. And what about the distance? And the distance is 3 kilometers apart. Okay, so that's the closest they ever get. All right, so again, this is pretty much a carbon copy of the one that we did in class, except, you know, the directions, I think that one, it came from the south. Okay, numbers might be a little bigger than, or a little bigger than what we did last time, not 100% sure, but this is essentially now you have the basic idea on how to solve these types of problems. Okay, any questions on this? No, if not, let's move on. Okay, next thing I had was 153 number 9. So let's see what 153 number 9 is. Oh, what is this? Another one of these. So it looks like this is a rectangular prism problem. So we've got the volume of this prism, reinforced concrete. Interior length will be twice the height. So let's keep that in mind. And then we have cost for the base, cost for the sides, and cost for the roof. So here, 3 different components, okay? Find the interior dimensions that will keep the cost to a minimum. All right, so that's pretty standard. It says to protect the table, the building code specifies that no excavation can be more than 22 meters deep. Okay, so H has to be greater than or less than or equal to 22, and it also has to be at least 1 meter deep, so greater than or equal to 1. So again, looks like we're working on closed interval. Okay. So on some of these, I'll probably do the algebra and the calculus, but I may leave it to you to sort of check the max and min. So let's see, this is page 153, number 9. Okay, and you know, if whoever asked this question can tell me what they had a difficulty with, that's sometimes can be helpful. So I've got rectangular prism, and it said the length is twice the height. So if I call that the height, then the length here is going to be 2 times the height. And they didn't tell me anything about the width. So there seems to be no restriction. So notice here, they did not say it was a square shaped or square based prism. So we can't assume that. So I'll leave that as W. Okay. And we want to minimize the cost. Okay. So if I'm not mistaken, there's a specific cost for the base, which was $40. So we're going to do $40 times the area of the base. And that looks like it's 2H times W. So 2HW. Okay. Then it was 100 meters for the side walls, $100 per square meter for the side walls. So $100. So the side walls, so there's this one here, which is 2H times H, so 2H squared plus at the back, so 4H squared. Okay, and then these side walls here, H times W, and then there's 2 of them, so 2HW. Okay, and then it was, I forgot already, 200 for the roof. So $200 for the roof, and again, that has the same area as the base, so 2H times W. Okay. So here we've got our cost using our areas and the cost per area. I've got my total cost, and I see here already that I've got 2 variables. So this is where they gave me that I believe it was 20,000. So 20,000 meters squared is our volume, and that's going to be area of the base times the height. So it's going to be, looks like 2H squared times W. And looking at what I have here and looking at what I have here, it looks like it makes sense to isolate W. So divide by 2, so that's going to be 10,000 over H squared. Okay. So any questions so far? So I would say again, very similar to the ones we've seen. The only difference here is that, you know, there's a little more complexity in the different parts that have different costs. So I think before I input this in, it would make a lot more sense to clean this up a bit. So what do we have? Please check my algebra here. So 80 HW plus 400 H squared plus 200 HW plus 400 HW. So that's going to be 400 H squared plus 680 HW. And so now let me put in for W 10,000 over H squared. All right. And so here, as we've seen, happens all the time. So we have 400 H squared plus, so 680 plus 1, 2, 3, 4, another 4 zeros. All right. Oh, all over H, of course. Okay. And I think this is as simple as we're going to get it. And of course, H is going to have to be greater than 0. So we don't have a closed interval this time. Okay. Any questions so far? No. Okay. So now we take the derivative. So 2 times, so 800 H, and this of course is 6,800,000 H to the -1. So it's going to be -1. So -6. 1, 2, 3, 4, 5. I think that's good. And then H to the -2, which of course is going to go down into the denominator. Now, if you're not comfortable doing what I did, which was kind of just as you're doing it in your head, putting things in the right place, you should definitely show an extra step there. Okay. And of course, we want that equal to 0. Clear out the denominators by multiplying both sides by H squared. So we have 800 H cubed minus 6,800,000 equals 0. So H is equal to the cube root of that. And let's see what that gives us. So that's going to be 6, 8, 1, 2, 3, 4, 5 divided by 800. Okay, and cube root. So that's going to be exponent 1/3. So notice how I don't even bother using the nth root button here. It's just easier to do it as an exponent. So it looks like it's 20.4. I think I remember something saying 1 decimal place. Okay. So now you're going to check, of course, that this is indeed a maximum. So here, if we put in 1, we got 800. Sorry, minimum. We're minimizing costs. So here we've got 800 divided by 1 minus 6 million. This is definitely negative. I don't think there's any debate there. So let's stick in 30 to check that it is indeed positive on the other side. So what do we have? We have 800 times 30 cubed. Okay. And that's clearly bigger than 6.8 million because that's 21 million. So be positive here. And since there's no other critical points, we know it goes to, oops, sorry, we keep thinking it's a maximum. It's decreasing to our minimum and then increasing always afterwards. All right. And so there we have it. Let me go back to the question and see what they're looking for. Find the interior dimensions. So we have that the height is 20.4 meters. The length was 2 times that. So that would be 40.8 meters. And then the width is going to be, where is it here? 10,000 over 20.4 squared. So let's calculate that quickly. Divided by 20.4 squared. And looks like it's 24.0. Okay. You know, this is probably the one that, you know, certainly we've seen lots of times where the algebra, the, you know, calculus is not particularly difficult compared to some of the other ones we saw before. Yeah, Severia, question?
Just a quick question regarding models and number lines. So in this case, I understand there's no need to really like draw the number line considering that this was a quadratic, but like in the event
Oh,
where
this is not a quadratic. This is not a quadratic. I did need to draw the number line. This is not a quadratic.
Sorry, okay, sorry.
Yeah.
I'm gonna rephrase what I said.
Yeah.
What I'm trying to say is like in the event where let's say it's not a quadratic or like I guess it's the exponent is greater than 2, then you would like to see like a number line, right? Because it
Yeah.
cannot be obviously it can't be that obvious that it's going to be like an absolute max or an absolute min because there can be also localities as well, right?
Exactly. Exactly. Okay. So that's a very special scenario where you're working with a quadratic function where we know a priori based on its the sign of the leading coefficient, whether that there's going to be an absolute max or an absolute min. So that's a very special case, which this one
Thank you.
obviously does not fall in. Okay. Any other questions on this one here? Okay, so this one here, I would say this is a pretty, you know, pretty typical type of question. Now you've seen this many times, you know, with little differences here and there, but by and large, it's the it's fine. So would you take off marks to drew a number line even though it was quadratic? No, no, you know. Again, though, that's where, because drawing the number line and doing the little explanation, it's not really that much more time. Okay. So this was 153, number 9. Okay, so I got 2 more here and then possibly that third one. So 248, number 7. 248, number 7. Page 248, number 7. And let's see what that says. 248. Oh, here they give you the equation. So this obviously will be a lot easier. So concentration of drug in your blood. At what time does the highest concentration occur within the first 5 hours? Okay, so let's write down the equation. So C of T is equal to 10 times e to the negative 2t minus e to the negative 3t. Okay. And here, highest concentration within the first 5 hours. So here, again, we've got, I guess, a closed interval because it could be anywhere from 0 to 5 inclusive. All right. So again, this is a much easier problem because I didn't have to actually come up with the equation. They just gave it to me outright. So this is where we're going to put our focus now on the derivative, make sure we're not making any silly mistakes here. So let's take the derivative. And so this 10, remember, is just a constant, so I can leave it out there. And so here, the derivative of e to the negative 2t is e to the negative 2t. But again, knowing where this is going, I'm leaving a little room so I can put the coefficient in front times the derivative of negative 2t, which is negative 2. Okay, then minus, okay, again, derivative of e to negative 3t is e to the negative 3t. Okay, but of course, the times the derivative of negative 3t, which is negative 3. Okay, and so there's my derivative. And as usual, I have to make this equal to 0. So the 10 goes because I can just divide both sides by 10. So let's see what we have here. Well, this is going to be positive. So I'll have 3 e to the negative 3t equals, and I'll bring that to the other side. So it'll be positive 2 e to the negative 2t. Okay. Now, I guess the best thing to do here is to, remember what we can do easily with exponential expressions. And we don't really have a rule for adding two exponential expressions or subtracting two exponential expressions, but we do have rules for multiplying and dividing. So what I'm going to do is I'm going to divide one of these exponential expressions, okay? But I'd like to end up, so this is where I'm going to be, I'm going to choose this very carefully. I'm just not going to do it willy-nilly. I'm going to choose to try to end up with a positive exponent. So if I divide this to the other side, I'm going to have to subtract the exponents, negative 3t minus negative 2t. I'm still going to end up with a negative. But if I divide it the other way around, when I subtract the exponents, I'm going to end up with a positive exponent. So that's what I'm going to try to do. So I'm going to bring these e's together, but I'm not going to do it via addition and subtraction like I would if it was 2x and 5x, because the rules I have for exponential expressions are with multiplication and division. So that's what I'm going to divide. So I'll bring the 2 to the left-hand side. So 3/2 equals, normally I probably wouldn't write this out, but let me write it out so I'm really clear about what I'm doing. And now I can use my exponent rules, okay? So here, -2 minus -3 is -2 plus 3. So this is just going to be e to the t. And hey, look what I've got now. I've got a single exponential expression equal to the number. I can take the log of both sides. And of course, I'm going to take log base e. So ln of 3/2. Okay. Any questions on what I did here? So again, just took the derivative, and I noticed here that if I wanted to bring these two expressions together, it made more sense. There we go. It made more sense to divide them than to try to add them or subtract them, because those are the rules I have for exponential expressions. So here, since it is a closed interval, I can just calculate c at 0, c at 5, so the endpoints, and then calculate c at ln of 3/2, which I'm not even going to bother putting in. I'm just going to calculate what that is. So ln of 3/2, 0.405. Oops, c at 0.405. Okay, c at 0 is pretty easy because, of course, e to the 0 is going to be 1 minus e to the 0 is 1. So 1 minus 1 is 0. So that's just going to be 0. Okay. If I put 5, well, that I am going to have to calculate. So let me do that here. So I've got, where's e on this thing? E to the exponent of, put in here, -2 times 5. So e to the -10. Okay, minus e to the -15. Oof, times 10. That's a really, really small number. So 0.00045. All right, and now let's put this thing into the function and see what we get there. So we get, I have to do this carefully here, e to the, and here I think I should open up some brackets, -2 times 0.405. Okay, then minus e to the -3 times 0.405. Okay, and then times 10 is equal to 1.48. And clearly that's the maximum. So let me see what they're asking for. It says at what time does the highest concentration occur within the first 5 hours? So after 1.48 hours, C of t is at its max. Okay, So again, we had to deal with some, ugly numbers, but other than that, it was fairly straightforward because we didn't have to come up with the function ourselves. All right, any questions? Zaveri, is that a question or is that legacy?
Yeah, could you just re-clarify how you got the 3/2, like toward in the middle part, please?
Oh,
It's-
so what I did is I wanted to bring all the exponential expressions to one side and all the numerical expressions to the other side. So I divided 2 on the left and I divided e to the -3t on the right.
Okay, yeah, I see.
Yeah.
It makes sense, thanks.
So in the same way that when you have, something really straightforward, 2x plus 5 equals 4x, minus 7, what do? You want to bring all the x terms to one side, all the numerical terms to the other side, but because polynomial expressions simplify via addition and subtraction of like terms, that's not how it works with exponential expressions. They simplify via a multiplication and division. Okay, so that's what
Sounds
I
good.
did.
Thank you for clarifying.
Yeah,
Why?
another question?
Why wouldn't it be after 0.405 hours?
Oh, that's the concentration.
think, yeah, I
Thank you.
think that's
Yeah. I just looked at the wrong number. Good catch on that. After 0.405 hours. There you go. Good catch on that. Yeah. No, the 1.48 is the actual concentration, the maximum concentration, which they didn't ask for. Very good. Good catch on that. See, there you go. There's the half mark I just lost for not being careful. All right. Any other questions on this here? No. All right. So what's the next one? 265, number 19. 265, number 19. So this says the hypotenuse of a right triangle is 12 centimeters. Calculate the measures of the unknown angles in the triangle that will maximize its perimeter. Okay, so I'll draw the diagram so you can see what we're working with. So this looks like it should be relatively straightforward. It's a pretty simple shape, 265, number 19. Okay, so what they're giving us here is right angle triangle. So again, obviously them drawing the diagram for us, simplifies our life a little. So hypotenuse is 12, and they call the other two sides X and Y, which of course we would need that since we're looking for the perimeter, but they want us to measure the angle. So the fact that they're looking for the angle is kind of an indication that you probably want to try to write your equation using this one angle. Okay, and if you look at what we're trying to minimize, so the perimeter is just X plus Y plus 12. Okay, very often we see that we try to write X in terms of Y in terms of X, depending on what information we have. But since it's theta we're interested in, and we've done a question like this in class, we're going to write each of these variables in terms of that third variable. Okay, and we'll have our equation in terms of one variable, and not just that, it'll be the variable we're interested in. Okay, and here hopefully you can see that the connection we're going to make is just the primary trig ratios. Okay, so we know that sine of theta is opposite over a hypotenuse. Okay, so if I were to write y in terms of theta, y is just 12 sine theta. And then similarly, cos of theta is x over 12. So x, which is the other thing I've got in my expression, is just 12 cos theta. All right. So now let's just input this back into our equation. So we've got 12 cos theta plus 12 sine theta plus 12. And since theta has to live inside a right angle triangle, we know it's got to be between 0 and pi over 2, not including the those two. Okay, so theta between 0 and pi over 2. All right. So let's again take the derivative here. So the derivative, so this is going to be through cos as negative sine, so it'll be negative 12 sine theta plus derivative of sine is cos, so 12 cos theta. And of course, derivative of 12 is just 0, and that has to be equal to 0. All right. So what we have, we can divide both sides by 12. So essentially, we end up with sine theta equals cos theta. Okay. And of course, this is a very nice equality because we should know. We know when sine theta and cos theta are equal in the first quadrant. Where are sine and cosine equal in the first quadrant? Who's going to remind me? What's that angle where sine and cos have the exact same value? It's one of our special triangles.
Pi over 4.
There you go. The good old pi over 4 triangle. 1, 1, root 2. Okay, so here theta is going to be equal to pi over 4. Okay. Now, of course, what we need to do is show that this indeed gives us a a maximum perimeter. So let's test here. So from 0 to pi over 2, we got pi over 4. So here, I don't know, I'm just gonna take 0.1. And what do we have? Where's our, so we have, let me make sure, yeah, I'm in radians. So negative 12 times cos of 0.1. Okay, and then let's add 12 times, oops, no, I did it wrong. It's negative 12 sine. Negative 12 sine of 0.1. Okay, and then now I'm adding 12 times cos 0.1. Okay, and that is positive. Okay, so pi over 2, 3.14 is about 1.57. So let's take, I don't know, 1.5. And so here we have negative 12 times sine of 1.5. And now we're going to add 12 times cos of 1.5. And we end up with a negative number. Okay. And since this is the only critical point in this interval, it's increasing to that point and then continually decreasing after that. Okay. And so now notice, by the way, notice what I'm doing after every question. I go back and I look and I say, what is it that they're actually asking for? It says calculate the measures of the unknown angles in the triangle that will maximize its perimeter. So the only thing I need are the angles. So here theta is equal to pi over 4. And then I guess I'll call this phi. Okay. But of course, if that's pi over 4, that one's also going to be pi over 4. And this is a known angle, so I don't need to specify it. All right. So nothing too fancy in this one here. It was just about, you know, this is what we needed. That was pretty straightforward. And just to make the connection that we could use our primary trig ratios to get the specific values or expressions in terms of one variable. Okay, yeah, Zavarian.
So for the number line, when we're using like a trig ratio or like a trigonometric type question, you're fine if we like put decimals like in between like those intervals, right? Like you did just now?
Yeah, because
Okay.
all we're doing is testing the intervals. We're not actually, even here, if I want exact answers, this part is just about testing signs. And remember what we said, it could be any value. And 0.1 is definitely between 0 and pi over 4, as 1.5 is between pi over 4 and pi over 2. So in this intermediary step, there's no need to pick something that's exact.
Got it.
Okay.
Thank you.
Yeah. Anybody else have any questions on this here? Yeah, Arthur.
This might be a silly question, but are we gonna be provided the special triangle in the was it the test that we have, or are we gonna provide like the trig ratio? Be provided the trig ratios too.
I mean, I gotta be honest with you.
We should be
probably-
knowing it, right? So
Kind of figure you should know it. I guess
Yeah.
If
I
you
mean,
need it during a test, I'd probably just give it to you without
Yeah.
selling it to you, because it's not, I guess, not technically part of the curriculum that we're learning. So I'd probably just give it to you outright, you know.
All right, thank you, thank you.
Anything else? All right, so we're pretty much coming up to the hour. I can take a quick look at this other one, which was page 157, number 16. So maybe I might not solve this one fully, but we can get the maybe the model in. So what is this one about? 157, number 16. Oh, this is not what I assumed it was. Oh, I thought it was one of those car questions. Oh, I didn't even realize there was a video for this. Maybe I just forgot to put it on. So it says you're given a piece of sheet metal that is twice as long as it is wide and has an area of 800 meters squared. Find the dimensions of a rectangular box that would contain a maximum volume if it were constructed from a piece of metal by cutting out squares of equal area on all four corners and folding up the slides. Okay. So this is, okay, I think there was a homework question on this in the first homework that would have been very similar. So this is page 157, number 16. So here they're giving you some piece of metal, okay? And what do they tell us about this? It's twice as long as it is wide, okay? So if I call X the width, actually no, because I think I might use X for something else. So here, here, this is the width, and then this is twice as long as the width, so 2W, all right? And what we know is that the area is 800 meters squared. Oh, so actually we'll probably be able to solve this outright. So the area is 800 meters squared. And we know that the area is just going to be 2 times 2W times W. Oh, looks like we can actually calculate. Okay. Oh, and I see, thank you. Somebody posted the video link there. You can look at that. All right. So here, divide by 2, W squared is equal to 400. So W is equal to, well, again, normally it would be plus or minus 20, but it would just be positive 20. So this is an interesting one because we actually were able to determine this directly. If that's 20, then it means that one's 40. Okay, so I guess they, instead of just giving this to us outright, they made us do our work to find it. So what are we doing now? We're cutting out corners on each side. And then what we're going to do is we're going to raise up each of those to create an open top box. Okay, so that means that this is going to represent the base of our box. Okay, because these things are being raised up. All right, so what I want to do is I want to maximize the what's it called? The volume of the box. Okay, so the volume is, I'll use lowercase letters so that I don't I don't confuse with these. So length times width times height. Okay, and what we don't know, okay, and this is what hopefully you would have seen in that homework question we did it, is what we don't know is how much of a square we're cutting out. Okay, so this is going to be our variable. Okay, so when we think about the length of the box that we're creating, it's going to be this length here. So what is this length? Well, it's 40 minus this little x and that little x. So 40 minus 2x. Okay, then the width here is going to be similar. It's going to be 20 minus this little x and that little x. So 20 minus 2x. Okay. And then the height, well, remember the height is, what are we doing? Is we're taking that square and we're moving it up. So the height is just going to be x. All right. And there is our, essentially our model for the volume. Okay. And then here we want to figure out what x can be. Well, x definitely has to be bigger than 0. And can you sort of see that x has to be less than half of the shortest length here? If this is 20, I guess I could have a very, very thin box that's very tall. But since I have to have an x on either side, those two can't add up to more than 20. So it'll have to be less than 10. And there's the model. So we see here that it's fairly easy because it's a cubic. Okay. But it is on an open interval. So when you're doing the work, make sure you are justifying that it is indeed a maximum volume. All right. And of course, when you take the derivative, please don't try to take the, product rule multiple times. Just multiply all this out, and then taking the derivative of the cubic would be very, very simple. Okay, so I'm not sure who asked this one. Any questions on that, or does that kind of answer it? Okay, so I'm going to stop the recording now.